Okay. So as a reminder, so next class, so Tuesday, the 18th, I will be teaching from a classroom in Gulf Park. And then Thursday, that would be the 20th, there is no class because there are no classes at all. It's fall break. Okay. Now, we've dealt some with Bessel equation previously. So what have we found? That if you have a Bessel equation of a non-integer order, then Frobenius' method gives you two linearly independent solutions. But when it's a Bessel equation of integer order, you only get one linearly independent solution. Because you have solution j sub n and j sub minus n, but when n is an integer, those are scalar multiple or plus or minus each other. So you really only have one linearly independent solution. Now we have seen a way of getting a second linearly independent solution, and that is by reduction of order. Unlike the non-integer case where you get j sub nu and j sub minus nu, your second solution in the integer order case is a very different form. And we're going to call that a Bessel function of the second kind, as opposed to function jn, which is a Bessel function of the first kind. Another name for a Bessel function of the second kind is a Neumann function. So for any order, integer or not, we can define a Neumann function this way. So what we have here is a linear combination of two Bessel functions of a first kind, of order nu and minus nu. The Bessel equation is a linear differential equation, linear and homogeneous, which means that any linear combination of solutions is also a solution. So because j nu and j minus nu are solutions, y nu is also a solution. Now, in the non-integer order case, this is well defined. We can just go ahead and use this formula, and that's it. Really, what we're doing is you're taking a linear combination of two solutions that are already linearly independent. So then, a linearly independent set of solutions would be, instead of using j nu and j minus nu, you can use j nu and y nu, because those are still linearly independent in the non-integer case. But things get more complicated when the order nu is an integer, because what happens, first of all, sine of an integer multiple of pi is 0, so we have 0 in the denominator. In the numerator, cosine of integer times pi, this would be equal to minus 1 to the nu power. Well, in the integer order case, j minus nu is equal to minus 1 to the nu times j nu. So we've seen that before. J minus nu x equal to minus 1 nu j nu of x. Nu is an integer. Okay, so because of this relationship, not only is the denominator 0, the numerator is also 0. So we have an indeterminate form, 0 over 0. So what we need to do is treat this quantity as a limit. So we leave the order nu as a variable, and we take the limit as nu approaches some integer n. And we want to make sure that check whether the limit that we get, first of all, does the limit exist? If the limit exists, it's at least non-zero, because we need a solution that is non-zero. So here's what happens. So here's my expression to start with, taking a limit as nu approaches n, where n is an integer. Now when you apply L'Hopital's rule, you take a derivative of a numerator and a new derivative of a denominator separately. So that's what happens in this step right here. We have pi cosine nu pi down below. Here we needed to use the product rule. That gives me these two terms. Now, as nu approaches an integer, this part is going to become 0. So you can forget about that. Now, as we move to this next term, we have cosine nu pi over cosine nu pi, those cancel. So we have 1 over pi derivative of j nu. Now for the remaining term, cosine of nu pi is equal to minus 1 to the nu when nu is an integer. So that's where this minus 1 to the n comes from. And we have a derivative of j sub minus nu. So now the limit simplifies to this. We no longer have a troublesome fraction. So this is something we can attempt to evaluate. Okay, so try to get a handle on what this is. And I'll just warn you up front, if you've not seen the notes yet, because you're going to get incredibly ugly. Do you agree? Yeah. Okay. Yes, I'm very grateful to Past Me for running all that. Okay, so here's the series definition of J nu that was established before. Using a gamma function, it's a generalization of factorial, the non-integer arguments. So what I'm going to do is substitute this series definition of J nu in here, and then do something with it. Try to simplify it as much as possible. One thing that we're going to make use of is what's called the digamma function. That's derivative of the gamma function over the gamma function. You imagine if we're taking the derivative of this with respect to nu, that's going to pop up. Let's gently just begin. So, okay. So what I have here is the derivative. So now I'm just going to be working with derivative with respect to n of Jn. Okay. And that's what I have here. Now to explain where this came from, it's too bad I don't have everything in front of me at once. Okay. Now, I will take the derivative of this whole expression with respect to nu. So where does nu appear? Here and here. So because it occurs in two different factors, I'm going to have to use the product rule. For applying the product rule, I'm going to take the derivative of this first. Now, the differentiation rule I'm going to use so I'll give a general rule here. a to the x prime is equal to a to the x natural log of a. That's where this log appears. So here I have x over 2 is playing a role. Well, I'm going to use a different letter to avoid ambiguity. So in this case, x over 2 is playing the role of my base, a. The exponent is 2k plus n. So I have a to the u natural log of a. And then by chain rule, you take the derivative of the exponent with respect to n, but that's just going to be 1. The rest of the series form of the Bessel function remains unchanged, because in this term, the only thing I'm taking derivative with respect to n is this. Now, admittedly, I have things written in a strange order here, because I have to take the derivative of this in the same way, take the derivative of j sub minus n with respect to n. So that leads to a similar term right here. It's just that wherever you see n over here, it's minus n over here. And then we have this factor of minus 1 to the n that came from here. Now, here we have a minus. Here we have a plus, because we're taking derivative of this with respect to minus this with respect to n. We have minus n here, which causes an additional minus to appear, making this a plus. So what I did for both jn and j minus n, took the derivative of this part here and this part here. And you see these have a similar form. Down here is where I complete the product rule. Now I'm going to take the derivative of this right here. Now, okay. When I'm taking the derivative of this, I'm going to get, so since this is in the denominator, I'm going to have minus 1 over this squared, okay, and so you see that there, times the derivative of this. Well, that's going to be the derivative of a gamma function. And remember, gamma function is equal to the factorial of this argument minus 1. So whatever argument you have here for factorial, you need that argument plus 1 for the gamma function. As I mentioned, you have derivative of 1 over something, you have minus 1 over that squared. That leads to this minus out here. And then this term is handled the same way. Taking derivative again with respect to n, but here we have a minus, that leads to additional minus causing this plus. So there's a lot to unpack here, algebraically. I'll give you the guidance for how all this came about. Are there any questions about how we got here before I did go further? I guess there's always the option to take my word for it, but I don't expect anyone to. And generally not a good idea. I'm very calm. At least at this point, certain things can simplify. For one thing, because this differentiation rule producing, you take derivative a to the u, get itself times the log factor, what we see here, not here. What we see here, aside from the log factor, that's just a Bessel function. So I have j of x and then times this logarithmic factor. And the same thing over here, plus minus 1 to the n. This is a formula for j sub minus n times the log factor. So that's a lot more concise now, thankfully. As for the other terms, here I have gamma prime at k equals n plus 1. This is my fallibility. I've already spotted a mistake. Be very careful about when I edit. Okay. Here I have k plus n factorial squared, which is the same as gamma of k plus n plus 1 squared. When you have gamma prime over gamma, that's the digamma function. So the digamma function absorbs one of these k plus n factorials. The other one is left behind. And I forgot to put that there. That square should not be there. And I don't change anything else yet. Same thing over here. Here I have k minus n factorial squared. One of those gets absorbed into the digamma function, k minus n plus 1, because here I have gamma prime at this argument. Down below I have gamma at this argument, squared. That's the digamma function. Next, Jn and minus 1 to the n, j minus n, those are equal. So I just have, that gives me 2Jn. So at least that part is quite condensed. And then, okay. I don't do anything with this summation, but with this one, I do form an index shift. So what I do is I decrease the starting value of k by n. So then whenever you see k in here, I replace it with k plus n, and then simplify as much as possible. What helps with that, the reason why it's helpful is, look at the powers of x over 2, they're now the same. Now, notice this summation goes from 0 to infinity. This one goes from minus n to infinity. So I'll have a summation, one summation from 0 to infinity. So I take this summation, and then all of these terms from 0 to infinity, and I'll combine them into one summation. And notice that, you look at how these two summations are distinguished from one another. Denominator is the same, x over 2 to the same power. The digamma functions, those are different. Now here we have minus 1 to the k. Here we have minus 1 to the k plus n. But here I have another minus 1 to the n. So this minus 1 to the n and minus 1 to the n will cancel, leaving 1. We still have minus 1 to the k, which matches minus 1 to the k over here. So now we can combine these summations where everything is the same except the two digamma functions. So I have that right from here for k going from 0 to infinity. Now I can't forget about terms from this summation for the other values of k, the negative values, from minus n to minus 1. So those are reproduced here. Oh, wow. Still way to go. Sorry. Okay. All right, now what I do is the next change I make, I perform another index shift. So now I increase the starting index by n. So wherever you see k, you now have to replace it with k minus n, which gives me all this. The rest of this does not change. um, now, oh, okay. Provided the next step, I need to use this result. That has a relationship between the digamma function and the gamma functions. Take this limit as he approaches a negative integer that condenses to this. So that's what I'm using to get from here to here. Now, all the minus ones, various powers, will cancel. The n and n, k minus k, then minus 1 squared. All those become 1, simplify to 1. I still have a factorial, a factorial, all that. And now there's nothing more that can be done. So start something ugly and have something now that's only slightly less ugly. As a formula for yn of x, where n is an integer. So what we see is it starts out with a logarithmic term times Bessel function. So Bessel function of the second kind is equal to the multiple of the Bessel function of the first kind times a log factor, and then we have these summations that involve a digamma function. So at least we have a formula for Bessel function of the second kind. Questions about any of the steps that ensued? Now, our goal here is to have two linearly independent solutions of the Bessel equation. That means you have to make sure that the two solutions are not scalar multiples of each other. The first solution being this plain old Jn of x, it's easy to see that our second solution, yn of x, is linearly independent of Jn. It's definitely not a scalar multiple of it, considering we have this log factor and all these terms added onto it. So now we have two linearly independent solutions. And if we look at what happens, if you can't, this Bessel function of the second kind is undefined at x equals 0 because of this log being undefined there. So Bessel function of the first kind is well defined at x equals 0. The second kind is singular. else left. It should be easier to get through than what I just did. Focusing on the n equals 0 case, things simplify a bit. And what happens in here, the digamma function, k plus 1, k is an integer, happens to be equal to this constant called the negative, what's called the Euler-Mascheroni constant, plus this expression hk. You recall the harmonic series, which is the sum of 1 over m and going from 1 to infinity. That series diverges, but you can define hm to be the sum, a partial sum of a harmonic series. So just summing terms from 1 to n. So that's certainly well defined. So where we see the digamma function, we're able to replace it with this. So now we have this somewhat simplified expression for y0, the Bessel function of the second kind of order 0. Now, when we look at Bessel functions of the first kind, found that it's possible to express them using an integral. We can do that with Bessel functions of the second kind, too. I won't go through the pain of deriving these, but for your reference, here's what they are. So we have two different forms of y0, different limits, and then we have this combination of integrals for yn. That's a function of the first kind, and expression similar to this, like cosine here instead of the sine. Okay. We saw that Bessel functions of the first kind satisfy a number of recurrence relations. Same is true of Bessel functions of the second kind. So these relations are exactly the same as what we see for Bessel functions of the first kind. And it's all because both these functions are solutions to the Bessel equation. I don't remember if I covered this earlier in this class. It's something that gets covered in a first differential equation class. That there's a formula for the Wronskian of two solutions of a self-adjoint ODE, where we have actually, in fact, the self-adjoint part is not even. Oh, okay. Abel's theorem applies whether the ODE is self-adjoint or not. But in the specific case where it is self-adjoint, we have a particularly simple formula for the Wronskian. It's some constant, admittedly unknown, divided by p of x. So this coefficient of y double prime. So what's interesting about this is we have an idea of what the Wronskian is, even if we don't know what y1 and y2 are. The only thing we don't know is what is its constant. Now, granted, if y1 and y2 are solutions, any scalar multiple of them is also a solution. But it would be nice to know what is the value of constant c for a specific case of y1 and y2 being equal to Bessel functions of a first and second kind. Now we'll take a look at that. So the Bessel equation is rewritten in this order. Normally it's written so that it has x squared in front of a second derivative term. But we write it this way so that the equation is self-adjoint. We need the coefficient of y prime to be the derivative of a coefficient of y double prime, and written this way, it is. When it happens, we look at for non-integer case, we have two literally independent solutions, j nu and j minus nu. So we know that the Wronskian of them is going to be some constant divided by the coefficient of y double prime, which is x. We just don't know at this point. Now we don't know what that constant a nu is. But it's something that it depends only on the order of a Bessel function. It would not depend on x. But the thing is, this right here is a function of x. So if we were to substitute a value in for x, because of these being equal, we could use that to figure out what a nu must be. Now it seems strange to suggest, okay, we can use any computing value of x since x equals 0, even though we're literally dividing by 0 right here. So it seems like an odd suggestion, but it's not as odd as it appears. Because what we can do is use these approximations of Bessel function for small x, because remember, a Bessel function of a first kind are non-singular or very defined at x equals 0. So, and certainly the closer x is to 0, the more accurate these approximations will be. To give you a justification of these approximations, I go back to where I have a full series written out right here. So if we assume that x is small, what happens is as k increases, then we're taking this small value, x over 2, and raising it to a larger power, because as k increases, this power is becoming more and more positive. So this is getting smaller and smaller as k increases. Not only that, we have k factorial, which grows extremely rapidly, and this is the evaluation of the gamma function, also growing very rapidly. So these terms, as k increases, get small extremely fast. And the larger nu is, the more rapidly they will decay to 0. So it's not unreasonable when x is small to consider, for instance, just the leading term, k equals 0. And that's exactly what was done here, in getting this approximation of j nu. And then they can take a derivative of that with respect to x to get this approximation, and so on. Okay. So now, these are the 4 ingredients in a Wronskian. So we can just take this times this, minus this times this, simplify as much as we can. And it turns out that, oddly enough, this is what we get. So now we have a value for a nu, so minus 2 sine of nu pi over x. Oh, wait a minute. That x shouldn't be there. I feel like less grateful to past me than I normally am. Mm-hmm. Yeah, because the whole Wronskian is this, but this is a nu over x. Okay. Now, what's interesting about this is, let's suppose that this is worked out for any order new. But when new is an integer, we get sine of an integer multiple of pi, which is 0. Quantity is 0. That would mean that this functions jn and j minus n, where n is an integer, are linearly dependent, although we already knew that. So that's consistent with what we've already seen. Now, using what we've seen here in conjunction with other recurrences involving Bessel functions, we have these relationships also. I don't recall if I assigned those as homework. I guess we'll find out soon. Okay. I've arrived at the end of the notes. Roll the pages far. Like a slog. So now let's leave plenty of time for any questions about this or about homework problems. A lot more questions come from the ones who are in this room, but y'all got nothing? Or any from out there? Well, good, it's exhausting, but okay. But well, good, because that was exhausting. Well, I guess between everything I was working out in my first class and then in between class, and then now. At least now it's good to do a little bit of post processing and rest my mind. So. Okay. I will see you from Golf Park on Tuesday.
No one in the classroom.
Then I'm teaching to an empty room.
So we're not meeting on
So Monday we will be.
Yeah.
Just not for Wednesday.
I was thinking Monday and Tuesday were the same day.
Oh,